Mm. I hope you can see everything. If you could please confirm.
Yes. Mm-hmm.
Okay. Okay, thank you. So hello, everyone. Thanks for coming. My name is Peter or Piotr Hofer, and I am an engineering manager at Antmicro. I will be talking today about our workflow, the workflow we used that was CI-based and using our simulator called Renode when we were working on bringing TensorFlow Lite and Zephyr together. Just a quick introduction about the company I come from. We're on the market for a little bit more than 10 years. We do everything embedded. So we work with AI systems in different areas, in agriculture, robotics, in automation, and you name it. We are very strong open source advocates, and we firmly believe that open source is the way to go if you want to push the world forward and the technology. That's why we are members of the Linux Foundation, of course, the Zephyr project, the Chips Alliance Open Power Foundation, and we are one of the strategic founding members for the RISC-V International. Our mission is to help our partners and our customers to embrace new methodologies and workflows using open tools, especially when in the industries where openness and open source is traditionally not present. So as I mentioned, we do a lot of software, but we're also doing our share of hardware. We have a lot of FPGA, IP and tooling experience, and we do tools like the simulation tool I'll be talking about today. If you want to see what technologies we are working with, you can see our website, and we have a technology showcase with, well, trying to list everything interesting that we're working on currently. So to the topic of the presentation. First, I will try to say a few words about the place of the AI in the IoT space. So I like this slide very much because it contains it's a headline from New York Times from 9 years ago, and it's of course very clickbaity. How many computers to identify a cat? 16,000. The article in its headline does not mention that it's not about identification, but training of a unsupervised training of a neural network, which is actually quite a complex problem. But of course, traditionally, machine learning and artificial intelligence is connected and understood as something that you do on big, very strong computers. So where's the place of IoT in this context? So we talk about tiny machine learning, which is traditionally understood as machine learning algorithms operating on the edge devices that is not very powerful and not necessarily connected to a stable power source. The idea is that whenever, as soon as you acquire data, you want to process it and to have some results from your machine learning workflow. So the reasons for this might be twofold. One is that you want to have the results as soon as possible without the delay of communication. And the second reason is that communication itself might be prohibitively expensive, for example, in terms of power consumption. Of course, small devices can't do much if you compare them to big mainframes. But you have to remember that we have many, many devices in each and every fridge, toaster, phone. Almost everything is connected nowadays. And of course, the trends will continue. So how strong a machine has to be to do reasonable machine learning? and what requirements does it have to meet? It turns out that not many requirements, because machine learning is mainly computation. So we need to have a way to acquire some data. It might be a sensor, maybe some sensors that you will combine together. You have to have a way to signal the results. So it might be a standard interface like a UART or some network connection, or it might be an alarm or an auto-destruction trigger or whatever actuator you come up with. So it's easy to fulfill these requirements. Practically every device, even when talking about MCUs, can provide these. So it's not really much, and every device can function as a driver for ML algorithm. Why should we use small devices? So the numbers I provide in the slide are not mine, and they are taken from an article co-authored by Pete Warden, who is lead of the TensorFlow Lite Micro team at Google. But of course, I don't care about the precise numbers here. I want to show you the scale. So if we're talking about computation, it was calculated by the authors of this paper that a single operation on hardware on an MCU class device can take around, let's say, 5 picojoules. If we take a small image recognition network from MobileNet version 2, it requires about 22 million operations to actually calculate something reasonable from an input. So one run is about 110 microjoules, and if you're processing about 1 frame per second, it is 110 microwatts. So if you have so this power consumption means that you can run an efficient machine learning algorithm on a battery-powered device that will last long. You don't have to have it connected to an external power source, which is important because we have many of such devices. They can be placed virtually everywhere, and yeah, they can do machine learning. So you probably all know what TensorFlow is. TensorFlow is one of the most popular AI frameworks out there. It was originally developed by Google and is maintained by Google, and it's open source, which we like very much. TensorFlow has a branch or a specialization called TensorFlow Lite. TensorFlow Lite targets mobile devices. By mobile devices, we mean, for example, your phones. So here we'll be talking about AI processing that is somehow connected to the applications that you run on your phone. What's nice about the TensorFlow Lite is that it can use the same models as TensorFlow that can be converted to TensorFlow Lite format. Also, as such devices are very often specialized and somehow they are employed with some additional machine learning accelerators, TFLite provides an API to use such accelerators. But this is, of course, not targeting the MCU class devices. It's targeting things that can run Linux-based operating system. But we have also TensorFlow Lite Micro. TensorFlow Lite Micro is optimized for very, very small devices. It relies on similar models as the TFLite I mentioned before. And it, of course, is designed to do only inference, not training of networks, but inference on very constrained MCUs. It does not provide the full functionality of TensorFlow, only a limited subset, but it's still enough to do very interesting processing. What is important in the context of this presentation is that TF Lite Micro is cross-platform, which means that it requires some hardware abstraction to to process to operate on a target system. Also, an interesting thing to remember about TF Lite Micro is that it is an interpreter. Interpreters are not very popular in the MCU areas, but of course we have interpreters in this space as well. For example, MicroPython, right? But it turns out that this interpreter approach is quite clever because your machine, well, your network, your neural network does not have to be compiled with your application. You can load it and possibly upload it over the air, so you can update it in the lifetime of your device, which is pretty nice. So, why should we want to actually integrate Zephyr and TensorFlow Lite Micro? This comes from our long collaboration with the TensorFlow team. It began somewhere around 2018. We had a first presentation with Bitwarden at the RISC-V Summit. And funnily enough, it was called Running Zephyr, RTOS, and TensorFlow Lite on RISC-V. But the point was that the presentation wasn't about running TensorFlow Lite and Zephyr at the same time. It was just, you could easily put it in two presentations and it would work just as well. So we didn't think about getting Zephyr and TensorFlow Lite together at that time. But our collaboration continued, and we had come to some results I'd like to share. So there are two possible perspectives we could look at this topic. We could take when looking at this topic. So one is that we would like to enable TensorFlow Lite Micro users to use Zephyr, for example, to provide hardware abstractions to run on different platforms, and to provide some operating system features, for example, networking, etc. In this case, it will be easy to track changes in the TensorFlow Lite Micro, because we would add this support in the TensorFlow Lite Micro itself, but it would probably be more difficult to track Zephyr changes. And the other perspective is to enable Zephyr users to use machine learning capabilities by adding TF Lite Micro as a module. This is, of course, also a perfectly viable use case. It just looks at the same problem from another perspective. And I will start with the second approach. It's not the one that we took, but very recently, you might have been on the presentation by Lauren Murphy 2 days ago on the same event. And she worked on adding TensorFlow Lite Micro exactly as a module to Zephyr. And this was merged very recently. So this is one option that you can take, and it works just fine. Our approach was different because we were more focused on the TensorFlow Lite side. So we first started working with a single target. Our target was a LiteX board, which is a soft SoC designed for FPGA use, with a VEX RISC-V CPU. That is, of course, RISC-V. This integration did not really require much from us, from the perspective of like the amount of code that had to be added. There are some infrastructural files that are changed in TensorFlow, for example, fetching Zephyr, fetching the Zephyr prerequisites, etc. But what you can see on the slide is a list of files that are added to a specific sample when you want to port it to Zephyr and the VEX RISC-V core. What is important to notice here is that the TensorFlow approach is to not to port itself, like the whole TensorFlow Lite Micro framework, but port specific samples, because they require different, for example, sensors, The magic wand requires an accelerometer, so your platform has to have an accelerometer, etc. But if you go to TensorFlow Lite Micro repo, you will find that all samples have their own ports for different platforms. But a port for Zephyr is fairly simple. It requires a project configuration file, which is known to you. It requires a make file, because TensorFlow relies on make files, which in turn, of course, calls the Zephyr build system. And the rest of the files are mostly boilerplate, actually. The accelerometer files are just there to provide an API between Zephyr and TensorFlow. The assert file is just a missing declaration, and the overlay file is just adding a sensor to a standard LiteX VexRisk5 setup. And the initial integration was actually done in Renode. This is a specific setup that is relying on LiteX with VexRisk5, but it could be made more generic to allow any Zephyr-based board. This wasn't our angle at that time. So our initial work, you can see the repository on the screen. You can visit it as well. It's online. Was to create a separate repo that will get LiteX, get TensorFlow, and use the integration that we introduced to provide like a full experience for a developer with proper instructions how to build everything from scratch. And yeah, this is still online, but we of course moved to more interesting projects. We had published a note on a speech recognition demo that we implemented using this integration. It requires some additional drivers and expanding some layers in the LiteX itself, but it was a pretty nice experiment. You can read more about on our blog. I mentioned Renode quite a few times already, so I should probably go to some details here. We used it for development, and we use it for testing, and we use it for debugging of our applications. Very short introduction. Renode is a software-agnostic open-source hardware simulator. It relies on blocks, so you can create your platforms using building blocks in runtime, and it provides full SoC simulation. So there is no compilation for Renode target. For example, Zephyr, you can compile for a very specific target for a specific simulator. But for Renode, you can use the same binary that you'd normally run on hardware because we simulate full SoCs. It provides some nice features, from which, of course, debugging capabilities and automation capabilities are the most important for us. You can do many different things with Renode. You can do, well, starting with TinyML development, but you can do architectural exploration. So for some pre-silicon work, you can analyze network protocols, which we've been also doing for Zephyr, etc., etc. There are many possibilities. And the thing about Renode is you can start with working just on a very limited CPU or at just an SoC level, but then you can expand your scope of interest to the whole board simulation, including sensors, inputs, outputs, etc., and then go to multi-node interconnected system with wireless wired communication. And it can all be executed in a single Renode instance. We cover several architectures. ARM and RISC-V are being the most prominent of them, but also OpenPower and Spark. And we not only work on the MCU level, but we can also handle big 64-bit platforms as well. We have a lot of boards that we already support. We have a long list of samples that you can just grab and run. And it's software agnostic, as I mentioned, so we run a whole bunch of different applications in there, starting from Linux through Zephyr and to just bare metal. Renode is used by several companies that you might already know. Zephyr is also a part of the Renode is also a part of the Zephyr CI, and it's also a part of the TensorFlow Lite Micro CI, which is makes us very happy. So if you wonder if you should use Renode, then I guess you should. If you develop any IoT-like system, if you'd like to have a proper testing capabilities, you want to do multi-node testing, then Renode is software for you. And what we try to promote is this continuous integration-based workflow. And I will try to show it in practice in a second on how do we use that in this TensorFlow and Zephyr integration. But our idea is to make the embedded development process as similar to the, let's say, regular application development as possible, which means that you should have a CI that verifies each and every commit of your work against a complex set of tests that are probably very difficult to do on hardware, especially if you're talking about multi-node wireless systems. Then you probably test them once in a while, but of course the capabilities are very limited in this case. So what was produced during this this work? First of all, as I mentioned, Renode is part of the TensorFlow Lite Micro CI, but we also created, in collaboration with TensorFlow, a set of repositories that show you how to start using this workflow and how you can treat them as some kind of templates. And you can fork, you can add your applications, and you can see what will be the results. I will show you this repository in a second, but there are a few interesting things there I would like to show. First of all, GitHub Actions, then some interactive collab samples. And what is also important is that it's tracking TensorFlow Lite Micro repository with an automated bot that just sends PRs that are automatically tested, so that you always know that the current version works fine, and it follows the latest master of TensorFlow Lite. So let me switch to another tab. So I hope you can see it as well. This is the repository, TensorFlow Zephyr Vector5 examples on Antmicro GitHub. And what you can see here, first of all, we provide some instructions how to start. So the instructions are relatively simple. You just do some initial setup, and then you just run build, and everything works out of the box. We also provide, as I mentioned, continuous integration setup using GitHub Actions, which you can also inspect here. And this CI uses Renode to verify if everything works as it should. So you can open one of these, and you can see the test results. You can see that Renode is running the tests. If you look at the CI files, you will see that we have a specific Renode action that allows you to use Renode in, let's say, 3 or 4 lines of code in your workflow file if you use GitHub Actions. But what we also provide in this repo, and I think it's pretty fun, is the Colab, Google Colab pages. One of this is here. So I pre-run parts of it just to speed up the Git cloning process. This is an interactive Jupyter notebook that you can simply run. You can see how easy it is to get Renode and just start it. You have to download it from our webpage. You can just take a snapshot of a portable package, unpack it, and then just run. Or you can install some testing requirements if you need. We also provide packages for Windows and macOS and popular Linux distributions. So,
Peter, I just want to let you know there's only about 4 minutes left.
Yes, I'm about to finish very soon.
All right.
But thanks for the note. So let me just run and you'll see what happens. So this collab setup allows you to see and to do the same thing that you'd normally see on when running on your local time. So here we have on your local machine. Here we have a library that talks to Renode, and you can see some output from the UART in this simulation. This is a magic wand example, so it should recognize a gesture. And hey, we have a slope gesture. Of course, you can provide your own data. You can change these files with your custom data if you want. And what you get also from this flow is some execution metrics. Of course, we run tons of instructions, so this is not very interesting, but you can see memory accesses over virtual time, you can see specific exceptions, and you can also see some peripheral accesses, so that you can see that the I2C was talked to very often, but the other peripherals not as much. So yeah, I could probably show a little some more things. We have also some examples using camera for different platforms, so you can just take your picture and see if it recognizes you as a person. But I guess that will have to wait for another occasion. So summing up, Renode is very, very simple to just start with. Go grab it, go visit our GitHub and our documentation, and go visit this repo. It gives you, it will give you many hints on how to integrate your project with Renode. How did we made this Zephyr and TensorFlow collaborate with each other? And of course, if you want, you can always contact us. We are very happy to help. I'm also happy to answer any questions, probably not today interactively, but if you have any questions, you can just contact us via email. Thanks very much.
All right, thank you, Peter. I'm going to go ahead and stop the recording.